The goal of this talk is to actually give you an overview of microscopy and to place near-field optics within the complex and constellation of types of microscopy that can be done today. And as you will see at the end of this talk, the microscopy is really, the future of microscopy is to integrate many of these thoughts together in order to be able to really go beyond what you can do today in microscopy. So, so let's go to the first slide. I know that there's probably this is a bit simple, what I'm about to talk about, but I think it's very important because you are going to need to understand the length scales and where the length scales end for particular microscopes. So the word nano is, used very much, but I don't know if everyone knows where nano refers to in terms of specific objects that we are used to hearing about. And this is a good example. Basically, what we're talking about are molecules here, and molecules are about 1/10 of a nanometer, okay? When I say these are small molecules, hydrogen is half an angstrom, okay? 1/10 is an angstrom, okay? So a small molecule like water is on the order of an angstrom. A larger molecule like an antibody, and you hear about antibodies all the time today, these molecules are on the order of 1 to, say, 3 to 4 nanometers, depending on size. The largest virus is 250 nanometers. The coronavirus is actually 120 nanometers. Bacteria are 1,000 nanometers or 1 micron. Now, this is the division line of an optical microscope normally, where you cannot really see a virus. That doesn't mean that you can't see a fluorescent dot that is a virus because someone added some molecule to make it fluorescent, okay? But the bottom line is that if you want to resolve a virus, that means see its structure, you cannot do it in an optical microscope. A bacterium, which is a 1 micron or 1,000 nanometers, you certainly can see in an optical microscope, and you'll see why in a moment. In addition, cells, say a cancer cell, 10,000 nanometers or 10 microns. The smallest cell is a red blood cell. It's 7 microns, okay? A dot that you put at the end of your writing is about 1 million nanometers, okay? And a tennis ball, okay, is about 100,000, 100 million nanometers, okay? So really a nanometer is to a tennis ball like a tennis ball is to the earth, okay? It's a huge range of dimensionality. Now, the thing that defines whether you can see something in an optical microscope is the wavelength of the radiation that you use. If you want to use visible light, the wavelength of a visible light, that means one wavelength, that means one peak in one valley, okay, is 500 nanometers. And that is in the visible range, that's green light, 500 nanometers. And it can resolve things that are half the wavelength. So it could really resolve at the ultimate 250 nanometers, although a regular optical microscope rarely achieves that without some help, okay? Now, the bottom line is that if you want to go to look at higher and higher resolution, you can go into the X-ray regime, And then you get very high resolution. You can even see specific atoms and their separation, because copper radiation, for example, that means radiation from a copper target, okay, is in the 1 angstrom regime range. And for molybdenum, it's even less than an angstrom, okay? So the bottom line is that if you want to go to shorter and shorter wavelengths, you can, but there are no lenses, there are no nice things that we can have in optics that you cannot have in these high energy short wavelength regimes. You can also go to the larger regimes, okay, and they have their own interesting aspects. For example, a terahertz can give you information that you would not be able to get with the X-rays or the visible light regime. And today, even in the terahertz regime, you can get super resolution using near field techniques. So really, the limit of optical resolution is not a law. It's just a limit based upon a criterion that was enunciated by Abbey and Raleigh. Basically, if you have 2 points, there's what is called a point spread function for that point. That means as light goes through it, you will see on your camera a distribution of light. And then you would see for the other point another distribution. And the criterion that was developed was that if the peak to the valley was 20%, you were able to resolve it. If not, you couldn't resolve it. Therefore, you could resolve a bacterium, okay? Well, but as you went to Paris, you had real issues. Near, if you see anything that you'd like me to answer, if you feel there's something not understandable, let me know as I go through it, okay? Now,
Sure, thank you.
Now you see this chart. You have the standard far field imaging. It has a resolution limit in XY of 500 nanometers. Z is very bad. Z is very bad, okay? You can do absorption of light, you can do fluorescence of light, you can do illumination at a point with this resolution. There's a great thing about an optical microscope, and that is that it images in parallel, okay? And that is such a wonderful thing that I've come to appreciate over the years, okay, that people don't necessarily appreciate when they're using the microscope. But the bottom line is that there's no super resolution, and there's another very important aspect of things. There's no direct phase. That means all your images are 2D, okay? You don't get any 3D imaging, okay? I'm going to start my video again, just in case, you know, the bandwidth would be okay. But if it isn't, I'll turn it off again, okay? Oh, you know what? It's not necessary. Because, okay. So now we go on, and we see how we can improve what an optical microscope can do. Now remember, there are 3 different things that the optics really is limited by, okay? The radiation, the wavelength of the radiation is a resolution limit, which is called the diffraction limit, okay? Another limit is that the lens cannot get close to the sample. Why is that important? Because from the sample, you have rays of light coming out that are what are called evanescent. That means they don't propagate all the way to a lens. And the lenses are far away from the sample, as you see from here. So this distance doesn't allow the lens to collect what are called evanescent waves. And these evanescent waves have higher frequency, and these higher frequency waves have more information and more resolution. Okay. In addition, there's a out of focus light problem. That means if I take, say, rhodamine, and I shine light through it with a laser, even with a lens, I will have light before the focus, I'll have light after the focus, and the resolution in Z is about 1.6 microns. So the bottom line is that all of these factors accumulate together to give you some of the things that are not so good about the optical microscope. So let us just do one thing, and that is, let us get rid of the out of focus light. Okay? So what do we do? Not we. This was a very, very important discovery in the many years ago, many tens of years ago. And what people do is this: they take an aperture, a small, not very small, just enough to make this a coherent beam, but you can use the laser actually by itself. And then you focus, and you have that 1.6 microns where different planes are being illuminated of the sample. Now, you don't change the lens at all. All you do is you put an aperture before the detector, which is just a photomultiplier. And what happens is that you are able to select, say, the plane, which is this heavy line, and not the broken line. And the broken line gets blocked from getting to the detector, and therefore you improve the spatial resolution by 2. And that doesn't even change the lens. It doesn't address any of the other issues, just getting rid of out of focus light. And it also improves Z, but not as much as you would like. So actually, confocal imaging can be done in 2 ways. One is you can scan the beam, and there's not much. I don't think nanomotion would be in that area. I mean, I don't think so. But you can also scan the sample. When you scan the sample, you get the highest resolution because all aberrations of the lens that are what are called off-axis aberrations are removed, and only a spherical aberration, which is an on-axis aberration, is included in the image. So the bottom line is you get the highest resolution by scanning the sample. Here, a nanomotion stage could be very good because it doesn't require, you know, a tenth of an angstrom resolution, things like that, but it does require, you know, a large area scanning. In addition, one of the bad things about all methodologies that increase resolution is that they are serial, okay? And we don't call confocal super resolution because it does not break really the half wavelength limit that I told you about. And there's no direct phase, okay? That means no 3D structure. In 1909, Sommerfeld first described how a radiating dipole.
Professor Lewis, but in confocal, by changing the position of the aperture, you can basically use slice. So you can take different heights and then generate from it a 3-dimensional structure. No,
that's not what I call 3D. Okay, that is 2D images at different depths in the sample. Okay, but if you want to correlate the structure of something with its optical distribution, okay, I mean its 3D structure, okay, that's not the way. You can't do it by that method. You get a series of 2D images at different depths in the sample, and that's not what is called
right. No phase. I understand.
no phase. Okay. So Sommerfeld in 1909, okay, described what is called a radiating dipole, okay, and he in his description, which was, you know, very, very important step forward, indicated that let's say you took a single molecule or a single atom, for that matter. Uh, in the atom, say you excited it with light, say this blue light here, and you got out red light, okay? What would happen is that at the very close region to the atom would be acting like a dipole, and that dipole would be radiating at a dimension that's very close to the dimension of the atom. Okay, so we're talking about angstroms here. Okay, so this was a very important development. So the idea to get super resolution from the time of Sommerfeld, I mean, Sommerfeld didn't indicate how you could ever.
Professor Lewis,
Yeah.
10.
Excuse me? For some reason, I can't. You started out nice and strong, but then you. Yes, I'm listening. Hello?
We are here.
Okay, very good. Okay, so so what happened is that in order to capture the resolution, you had to think of a way to make a dipole that you could in fact irradiate with regular light, and that dipole would then start to irradiate by itself, and it would then have the dimension of the dipole, and then it would actually diffract out from that dimension. Now you must understand at this point in history, the only things that really capture light were lenses and mirrors and prisms. Okay, this was a new way to think about how to capture light. And the first paper that did this was a paper that I published in 1984, okay, where we connected, as you see in the abstract here, to the near-field imaging issue. That means that we were the first people to really understand that we could take Sommerfeld's idea of a radiating dipole and capture it in a methodology that gave us some hope to make a microscope out of it. It took nearly 80 years for someone to realize that what Sommerfeld did could be applied to imaging. Okay.
Just a comment. Some people are asking me. I see that Nanonics team are also on the line. So don't worry, guys. In Nanomotion, I see Rima on the line and others. So the names that are not Nanomotion are Nanonics names.
I'm sorry. I said if I'm going to give it to my friends at Nanomotion, I should give it also to my family at the same time. Okay. All right. So so let's continue. So the idea was, how do you make a point dipole that you could translate, or you could translate the sample such that 2 points, which were smaller than the dimension of half a wavelength, could in fact be resolved. Okay. The idea that we applied was to make a opaque screen with an aperture that was, in 1980, 300 atoms across. Okay. But we had to, make such a hole. We had to actually show that such a hole could pass light. Okay. And then we had to be able to learn how to translate it relative to a sample that was even rough, okay, in order to make a microscope. So the chance of all those things happening in my lifetime was close to zero, I was thinking, okay. But in any event, okay, we were able, by 1981, okay, actually to write a proposal, and here's the first page of that proposal, to the National Submicron Facility. And these two people were experts in electron microscopy. John Silcox was from the Cambridge group, and Michael Isaacson was from the Chicago group of CRU, You may have known his name. So these were real experts in electron microscopy. And there was a new facility by the National Science Foundation at Cornell. And using that those equipment, we did the first electron beam lithography, and in such a way that we could see the apertures with the electron beam, and then take those same apertures and see where the light was coming through. And I remember the night that we took the first apertures after nearly 3 years of trying, okay? And we saw light through what we knew was a 300 angstrom aperture. So this paper was written. It was, we predicted correctly what the resolution limit would be for such a type of a microscope. It would be 50 nanometers. And we are, you know, no one has ever beaten that for this type of microscope. And really, we were very close to the exact number. There was another paper published in the same year, okay, by a man called Detector. And this was from the IBM group that had invented the scanning tunneling microscope. And what Detector called this microscope was an optical stethoscope. They didn't relate it really to the near field because, or to Sommerfeld's work. And calling it an optical stethoscope indicates that, because a stethoscope doesn't have any evanescence to it. That means you have a small aperture at the end of a long tube, but that small, that imaging methodology is with acoustic waves, and those acoustic waves always are propagating, even through a small aperture. So the physics is completely different for a near-field microscope and an optical stethoscope. In any event, one of the things that we saw was that we were seeing more transmission through the smallest apertures than what was theoretically predicted by someone at the university I was at, and that was Hans Bethe. Hans Bethe was the head of the theoretical physics group at Los Alamos National Laboratory during the making the bomb, okay? And he worked under Oppenheimer, but he was the head of the group. He eventually won a Nobel Prize for understanding the nuclear reactions of the sun. And he had done the first calculations on electromagnetic radiation through small apertures because they were very worried that some of the radiation would go through small apertures and really make the bomb not work the way they wanted it. So, as I said, from Galileo till near-field optics, there were very limited palette of things that could manipulate light. And in fact, we tried very hard in those days to get funding for it. And here is a letter. Dear Professor Lewis, thank you for your letter of July 21st, 1982. I am sorry to tell you that after all, I do not think your proposal for research on the interaction of tunable lasers with small apertures would qualify for venture research unit funding. As I mentioned during our discussions when we met at Cornell, we are seeking to support that fundamental research for which we imagine a substantial practical outcome. The research you described certainly meets the fundamental criterion, but I have had some difficulty in imagining an outcome of sufficient magnitude to justify an involvement. You mentioned scanning optical microscopes, but optical laser devices with resolution of λ/2 are already on the market. Now, you can't be too angry with this man, because in those days, there was no plasmonics. There was no structured light that was shown to be able to be, produced. There were there were no photonic band gaps. There were many things that were not known in those days, okay? And there were no papers in 1982 on near-field optics. And today there are hundreds of papers with 60% growth rate, okay? So after you come up with an idea, you have to translate that idea from fundamental discoveries into something that you can practically use, okay? And so the question was, how do we do this? Okay. And what was exciting about this new type of optical microscopy is that it solved the two other problems that I mentioned to you. One is the 3D structure, which you could get automatically, and one was the ability to get rid of the out of focus light. And so in 1986, we published a method where you put an aperture at a tip, and that tip could, in fact, track a surface, okay? And this idea actually came together with one of my first students in the field called Alec Haratunian, and together with Eric Bethe, who was a second student in the field, and Michael Isaacson, who was the electron microscope person. The same year, okay, I think that this was published in May, was received in May, but in March of that year was the discovery of one of the most important instruments that we know of the past century, and that's the atomic force microscope by Binnig, Quate, and Gerber. And Binnig was the one who originally invented the scanning tunneling microscope. And I believe, and this was really a watershed discovery that has led to many, many things, and certainly has led to near-field optics. So how does this microscope work? You basically, in the simplest version, you take a cantilever and you take a piezo, usually a cylindrical piezo, that can move X and Y and a little bit in Z. And you bounce a laser beam off that cantilever onto a position-sensitive detector. The position-sensitive detector essentially is a very sensitive device because it looks at the distribution of light on the 4 quadrants of the detector, actually 2 of the quadrants, and then it ratios them when everything is stable. And then you can bring the sample, let us say, up to the tip, and the surface forces start to make this bend. And when this bends, the ratio changes. That is sent to a controller, which then adjusts the piezo such that the piezo now reduces the effect and brings the detector back to its original position. What does that mean? It means that you initially have it reflecting. These 2 quadrants are being affected for various reasons. I won't go into why only 2 quadrants, but that's the fact, okay? And then you have these controlled by sent to a controller, which controls the high voltage on the piezo, and the piezo moves the sample up or down to bring the photodetector signal back to what it was. And how much the piezo was moved is your image. That means you actually have a calibrated piezo, and you know that you moved it 10 angstroms, 5 angstroms, 10 nanometers, 100 nanometers. How much you moved it, that was exactly the topography of the sample that you were, in fact, investigating, okay? And then you displayed those voltages on a screen, and that's your image, okay? Now, the bottom line is that you can see even in the microscopes that are, even today, this is, I think, still available, you can see this is the cylindrical piezo, okay? But the point was that these microscopes, even today, okay, most of them have no interest, or not no interest, no concept of how to do this effectively to integrate with optical microscopy. And the integration with optical microscopy is exactly what I told you in the beginning, that you don't have near field optics, and you don't have what is called far field optics. That means the lens is far away from the sample. You have some combination that will give you much more than what the individual will. Now, this is an AFM of a transistor, okay, that we obtained.
Can you repeat the last sentence you made,
Yes.
please?
What we see here is an AFM, okay? And I said here that this AFM has little really in it that says, you know, I really want to integrate with an optical microscope, okay? It's blocked from the top, blocked from the bottom. And many of them are like that, okay? And however, when this AFM idea is integrated with near-field optics, and if you built a machine that could be totally integrated into an optical microscope, AFM already is contributing to giving you optical super resolution. This is I wouldn't call it a naive thing, but it's basically showing how these techniques are synergistic with one another, okay? But the synergism is much more global than people realize today, okay? And that is that, as you will hear at the end of this talk, if you start putting the information you get from these different microscopies together, then you have a chance of achieving even better resolution and better methodologies for resolving the issues of microscopy, which are looking at the optical distribution and the 3D structure, okay? So here is an AFM of a transistor, okay? And you see that an AFM looks at the surface. You can't look underneath, say, the silicon oxide. There are transistors there, but you don't see them, okay? 1986 was a watershed year for me, since I fulfilled my dream of Aliyah, okay? And at the same time, as I was building my lab at Hebrew University, people were using near-field optics, started to use near-field optics, and they used the dipole of this aperture, okay? And they started to see that this was a very powerful tool, okay? One of the people who got his PhD from my group and then went to Bell Laboratories, which at that time was one of the premier laboratories in the world, okay, started to build a near-field microscope in 1986. And after I guess it started, I was basically made Aliyah, and then he was still in the lab till another year and a half. I used to go back and forth, and finally he applied his microscope at Bell Labs to be the first person in the world to see a single molecule at room temperature. People had seen a single molecule emission at low temperature, but no one had seen a single molecule emission at room temperature. And Eric Bethe was the first one to see it, and for that he was awarded the 2014 Nobel Prize for single molecule detection. And you can see how exciting and interesting this result was, because every molecule is a dipole, and the dipoles are distributed on the surface in 360 degrees. But your probe is a dipole in only one direction. So as the molecules interacted with the radiation that was coming from one dipole and entering into another dipole, okay, you can see that the molecules which were separated one from another, there's no super resolution here, okay, was like these two have different intensities of emission, because it depended on the integration of the dipole of the probe with the dipole of the molecule. The dipole of the molecule could be over 360 degrees relative to the dipole of the probe. And from that, he was able to calculate actually the orientation of the different molecules that he was seeing. So we today have a very interesting combination of techniques that can, in fact, give you a super resolution. In addition to the parallel imaging or standard optical microscopy, you have confocal, which I said is not super resolution. You have another microscope which is called STED, which I will talk about in a moment. And there's another microscope called PALM or STORM. And there's another microscope called SIM. And then there's NSOM. All of them are serial microscopes. Okay. So what is STED? STED is very interesting because you have two beams. Say a blue beam that excites a molecule in a sample that is fluorescent. And then you have, at the same time, a red beam, okay, that is called the depletion beam, that depletes the molecule in all regions other than the center. So it's like a donut. So you excite with blue, and then you deplete all around, and you're left only with a smaller point of light, okay? At the ultimate, let's say if you can shine tons of light and you study diamond, or which are, NV centers. I don't know if you know what an NV center is. It's a nitrogen vacancy center which emits light in diamond, okay? You can get even 30 nanometers with STED, but you need so much light in order to do it that you'd kill anything other than diamond, okay? There's another technique that was invented by Eric after he was at Bell Labs. He went to the Howard Hughes Institute, and this technique is called Photoactivated Localization Microscopy. Now, what you have in photoactivated localization microscopy is you densely label with a fluorescent molecule a sample. And then you shine, this fluorescent molecule is very unique because you shine UV light on it and it becomes visibly active as a fluorophore, as a fluorescent entity, okay? So now you, let's say, give one pulse of light, which is in the UV, and 3 of those molecules have become fluorescent in the visible. You localize those molecules. What do I mean by that? I mean that you have a stage with a very good closed loop, and you look at the distribution of the emission of those 3 molecules which are far apart from one another, okay? And you see the distribution, and you see that there's a peak and there's a distribution, just like I showed you before when I was talking about resolution. And that's called a point spread function. And the center of the point spread function has been determined to be the local point of the molecule. So you can very accurately localize these 3 objects. Then you give another pulse of light at another color and make them dark again. Then you give the UV pulse again, and you get 3 more molecules. And you localize them very well. And then you do this over and over again 20,000 times, okay? And you can, in fact, tell the distance between molecules that are close together because you were able to look at them individually, okay? And not have to resolve 2 points. So
Shechtman is working on it in MDM, no?
no, he's working on point spread function, trying to analyze the 3D point spread function. Remember, I told you that in Z, the depth is very large. Okay, the resolution is very bad in Z. But there's, just like you have a point spread function in X and Y, you have a point spread function in Z. Okay, he's trying to understand that point spread function and then trying to get less out of focus light information to get higher resolution. Okay? That's what he's doing. Now, there's still another method, which is really an elegant method. Okay? It's called structured illumination. And this is the place where, where nanomotion stages are used. Okay? And in fact, here's one of the references. See, nanomotion Yokneam. Okay? So in order to understand structured illumination, and I put the reference here before I explained it to you, because now I'm going to explain a few slides, okay? And to keep your attention, I thought it's better to show you that your stages are used in this field, okay? They're not used in POM, okay? I mean, as far as I know, okay? And that is because you need very high resolution probably, although I don't understand that fully, but let's say they're not used, right? As far as I know. Maybe I'm wrong, okay? Now, what happens is that you have an object, okay, in a microscope, and you have a lens, and you have a tube lens which makes an image, okay? Now, there is another plane in a microscope. It's called the Fourier plane. In the Fourier plane, all of the phases that were in the object actually come to the Fourier plane, and they intersect one with another. Not every ray intersects with every other ray, but they intersect, okay? You can, in fact, if you had a beam splitter, bring out the Fourier plane into its own image of the Fourier plane. That means it's not an image, it's a distribution of interferences, okay? That distribution of interferences actually undergoes a Fourier transform with this lens, which is the tube lens, to make the image that you see. And when the tube lens does that, it gets rid of all the phases. At this point, you have the phases of light, because you have how the interference of one ray is interfering with another ray, which is due to the exponential component of the electromagnetic field of the light, okay? Now, if you have an object, which we will call f of x, and you have a Fourier transform of it, you get an object which is described in terms of spatial domain, in terms of the frequency domain, okay? Now what happens is that you can take this object in the spatial domain, and let us say you multiply it by putting together with it another distribution of light. You multiply that distribution, g of x, with f of x. In the Fourier plane, you have a convolution, okay? I'll show you what that really means in a moment, okay? Basically, what structured illumination is you take f of x, and you put in front of f of x a grating. You illuminate through a grating with higher frequencies. So the grating is near the sample. You try and capture those higher frequencies that I told you were lost because you are not in close with a lens to the surface. And you have a convolution of the Fourier transform in frequency of the sample and the Fourier transform in frequency of this, the additional, say, image that, I'm sorry, the additional grating, this is a grating, I didn't tell you that, it's a grating that you impose on your sample. So this is a grating really, okay, with higher frequencies that you impose on your sample, and you get a convolution of the sample Fourier with the grating Fourier. And so what this really says is that in a lens, you, for various reasons, don't collect all of the light. You don't collect the evanescent fields. Some of the light goes out of the lens because it's an aperture, okay? And you usually see a particular frequency of light, in the Fourier plane. But if you now put another imposed, say, grating on your sample, and that grating had some sinusoidal behavior with higher frequencies, etc., you would in fact be able to get a convolution of these two functions in the Fourier plane. So what does that mean? It means that you take a diffraction grating, you put it close to the sample and you illuminate it. The illuminated sample, which is fluorescent, with that diffraction grating, for example. Now, in image space, this is your image. But in Fourier space, this is what that sample looks like. If you look at a direct image of this, you see that it's a grating. In Fourier space, this is what it looks like. There are two dots in a central maximum, okay? And this convolution looks something like this, okay? What does that mean? If you go out in frequency space, you see that as a result of the convolution, you are actually increasing that frequency space. But that's not enough, because you when you have a dark line and a white line, what about the things that were under the dark line? So you have to move that grating at least 3 times, okay? And that's not enough, because you have to rotate the grating at 60-degree angles and do the same thing over and over again and accumulate the images. And then you can get the type of resolution that, let us say this is confocal. I'm sorry, this is black and white, but it doesn't matter. It's gray levels anyway. This is, say this region here, okay? You can see over here. And this is in STED. Structured illumination is even better than STED, okay? This is structured illumination with 2 different types of gratings. But all of these methods require huge amounts of fluorescent dye and lots of light. So even though you may hear that people are studying things that are live, the only chance, even the small chance of doing it live, is with structured illumination. And that means that if you're doing biology, which is a lot of the optical microscopy that people are doing, okay? And one more thing is that you have to use a lot of light. So both, you need a sample that can stand this type of light. Now we come back to near-field optics, because this has the potential to do some of what I'm talking about in terms of palm and storm and come up with something else. And that is that in palm, storm, and sim, okay, you do not have any solution to the Z problem.
Without bleaching the fluorescent dye.
That's terrible. In all of those methodologies, it's bad news for the Jews, okay? In near-field optics, that's not the issue. You'll see what I mean in a minute, okay? There were other issues, okay? So I showed you this piezo, and I showed you this, that it was not integrated into optical microscopy. Not only was it not integrated, but all the probes that people used, except for one, essentially block light from the top. So if you have, let's say, a tissue sample, which is very scattering, okay, you couldn't see it. Or if you wanted to put it in an electron ion beam machine, you couldn't do it, okay? Or if you wanted to put it in a Raman microscope, you couldn't put your, what would be near-field microscope in a Raman microscope. So in fact, I know you are experts, and I feel terrible saying this, but I believe we were one of the first people to make a flexure scanner in the world, I think. I'm not sure. Nir can correct me if I'm wrong. But what we did was we took these piezos and we place them as a quadrant of 4. So what was a Z, which was only very little, and you stretch a piezo, you know that you have very little Z. Here, the Z was the same as the X and Y. So all this type of scanner has X, Y, and Z, which is exactly the same. Okay, and the Z can have ranges of many tens of microns. Okay. In addition, we focused on glass fibers, which are very, very important for uh, light, are also unique and wonderful for AFM because you can bend them in such a way that none of the outer rays of the lens can be are blocked. And it's really the only method that we know today that can do that. And we over the last 23 years of nanonics, we have focused on nano-optical light sources with gold nanoparticles for plasmonic probes with 2 wires in glass to make a nano heater or a thermal conductivity or to make a thermocouple, a metal wire of platinum in glass, other methodologies, what's called scanning electrochemical microscopy, and even deposition. And here is a good example of a deposition. When you get the presentation, you'll see this is a 15 nanometer line written with one of these pipettes that has copper formate solution in the pipette. And when it's deposited, the copper is reduced by the formate ion. And as a result, you get copper metal between these two contacts. It's a very important methodology. It's called fountain pen nanolithography. It has many, many more functionalities than dip pen lithography. Okay. One of my students, Talia Yeshua, was one of my last students, did really a superb job with this area. Also, one of the people I saw that is on here is Rima Bethe, and she worked a lot in this field. Now, the importance of this angle for optics is already realized in papers published with nanonic systems in 2003. It says, in our experimental configuration, the tip apex is not shadowed, as the laser beam is a focus beam with a converging angle of 26.7, while the half angle of the tip is only about 4 degrees. This was apertureless near-field scanning Raman microscopy using reflection scattering geometry. Again, it highlights that if you work hard enough, you can in fact reach integrations that give you more information than what you would have expected from the individual microscope. Moreover, what's very exciting about this methodology is that you can bring these probes in physical contact with one another. So you can have more than one probe. And in fact, you can see this is the probe, this is the lens. You can have all sorts of illuminations, side illumination, for example, if you want to have a plane illumination, which is very important in biology today. You can have multiple probes, okay? And you basically have everything with a completely free optical axis. And customers, even 6 years ago, were able to do what I just told you. Collisions between both tips were effectively prevented by a proximity detection mechanism based on mechanical interaction between both tips. The minimum distance between both tips is reached when both tip coatings touch. This is from Klein et al. 2014. Now, I'm not going to go into this, okay? Many papers have shown that with these probes, you can get very high resolution force sensitivity. down to the single piconewton regime. And in fact, customers of Nanonics have shown that you can detect single photons with the force sensing capabilities of this system. And I'm going to just skip over all of that. Okay. Now our systems go into SEMS. This is the whole AFM, just a flat scanner of 7 millimeters high. In this case, this small version has a XYZ range of 35 microns, okay? And you can watch the probe actually even being pressed against the surface in a SEM and see that nothing has happened to the tip of the probe. It's very hard to break glass in these dimensions. And I can show you.
Aaron, so this is the tunable fork, or this is a different probe than what you gave
No, you're
Booker?
right. I'm coming to that in a minute, okay?
Okay.
So you can see here the approach, a movie of the approach of the probe to the surface. It's a smooth, beautiful approach, and that's because of what Near is actually talking about right now, okay? But before I get into that, what's very important in the Z range is that you can deal with AFM with real samples. Here's a cardiac stent, 73 microns. Here's a razor blade, 67 microns, etc. Here is being able, because of the tip is exposed, you can look at sidewalls and you can even look at undercuts in the sidewalls, which is a very important thing. I won't go into it, but the noise is very low, very low, very low. And now this is what Near was speaking about. There are two methods of feedback in AFM. One is the one I explained to you, where you have a laser and a PSD. But there's another method, which today is known as the best method available, and that is tuning forks. And Nanonics, in 20 years ago, realized that and started to focus on how do you make tuning forks work in all environments, including liquids. And tuning forks have no jump to contact. These cantilevers are so soft that when you come close to the surface, they jump to contact within 5 nanometers of the surface. You can't look at the last 5 nanometers. There's no adhesion ringing when you pull off the cantilever. Very sharp frequencies, okay? And very important for optics, no feedback laser noise, okay? But no feedback laser noise is very important for many things other than optics. But before we talk about that, the systems can be applied together. Here's a paper published by a group. They used oxygen gas with our nanopipettes to oxygenate gallium nitride while measuring with a second probe the exact point, the Kelvin probe, that means the chemical potential change in the gallium nitride by the oxygenation of it. And here is a case where you wouldn't expect the optical background to be artifactual. It's in electrical measurements, because the beam bounce feedback generates carriers in the semiconductors and therefore causes artifacts. And this is a multi-center study at Stanford, Germany, China, Portugal, and 7 different AFMs. And they say, on the contrary, the MV4000 AFM simply has no laser, as it uses piezoelectric feedback system called a tuning fork, collecting electrical information of the sample in the complete dark, something not possible with most AFMs. And now we come to near-field optics, okay? And near-field optics is a flower that has really exploded over the years, okay? And I'm going to just take a few of these flowers just to give you an idea. The first flower that I'm going to take is reflection, okay? I'm going to show you what a near-field optical microscope is. Okay? You see, when in this movie, you see that little point of light? This is being scanned over transistors. And as the index of refraction changes, okay, you see the flickering of the tip of light. That flickering is collected by a lens. So you have a laser going through the probe. You have a flickering, which is collected by the lens. It's put on a detector, okay? And you make an image of the distribution of light while obtaining the AFM. This is what a probe looks like. A probe is a long fiber. One end is the micro world. One end is the nano world. Okay? You put that nano world onto your samples, onto your tip mount, and these are our scanners. Okay? Very thin scanners. You can even have two scanners with a completely free access.
So this is not parallel imaging. This is a place where precision, fast actuation will help.
Absolutely, absolutely, and you'll see what I mean by that in a moment. Okay, and what's very important about what you just said is that as we know from the MDM that Bethe is working on, he had these ideas of having the ability to have a probe which has, you know, many resonances, okay? But only a tuning fork has really that ability. That's why he's stuck with nanonics, okay? Because without our tuning forks, we can't do it, okay? That's the bottom line. But here is what's exciting about near-field optics. Near-field optics is not only a surface tool. Get the AFM, like I showed you here, and as I showed you before, the same AFM with the near-field optical probe as it's scanned. But the near-field optical image shows that you can see underneath that silicon oxide. Okay? And that's a very important thing in microscopy. There are many surface tools, but there are very few near surface tools. I wouldn't call an optical microscope a near surface tool because it has that 1.6 micron problem in Z. Okay? And you get very high resolution underneath the silicon oxide. I won't go into that, but Near knows what that can tell you about thin film thickness. Never mind. Now we're talking about nanometric illumination. We talked about reflection. Now we're going to talk about nanometric illumination. This was one of the first papers published with our system. It was a series of silver nanoparticles and a fluorescent bead. The lens in our systems can be placed independent of the probe, and what they did was they shine light on this, on this, on this, each 50 nanometer particle, and they imaged the fluorescence to see how the intensity of the fluorescence changed as you moved from one particle to another in order to understand what is called plasmonic transport of energy. So you shine light at one point in the near field, you need a near field probe, and then the plasmons actually interact between the particles. Eventually they reach this fluorescent particle, they're converted back into fluorescence, and they're collected here. When I made this slide, it had 1,800 citations. Today I went by chance just 2 days ago to see this paper. Yesterday is 2,500. Okay, it jumps by about 1,000 every 2 or 3 years. Okay. This is another paper done with silicon nanoparticles and the same methodology. I won't go into it, also with nanonics. This is a very interesting application of illumination. Basically, it was done by IBM with our system. It may have many, many more citations now. It's a graphene transistor. And with a near-field optical probe, you can put a point of light, point of light, point of light all along here and make an image of the photocurrent that you get at different photovoltages, because you want to understand how the contacts are affecting the graphene transistor. Okay? Now we are going to speak about luminescence, fluorescence. Okay? And here is an example. This is, you could take, we even make low temperature systems. You could take, this is an indium concentration in indium gallium nitride, and in gallium nitride, I'm sorry. So you have indium and gallium nitride, and the indium is diffusing. And as the indium is diffusing, the spectrum is changing, because you have indium gallium nitride as a result, and the intensity changes. So you can, in fact, measure as a function of distance from this indium location how it's diffusing. You can look at organic materials. These are organic nanorods, okay? And you can see here that the nanorod is, this is the structure of it. That's this nanorod, okay? Do you see these three guys here? That's these things. You see this? That's this, okay? Do you see this wavy area? That's this wavy area. So you can correlate exactly the fluorescence. The fluorescence is a little worse, quite a bit worse than the AFM, okay? But still, well, it's 70 nanometers. Okay. Now, here's a very interesting situation.
Aaron, we are really excited, but I know that some of the people have other
Yep.
obligations. So let's take 5 to 10 more minutes, okay?
No problem. I'm actually near the end. Okay.
Okay.
I'm not going to do that whole circle. This is the last one of the circle I'm doing. Okay. Now,
And also, we forgot to tell the team that there is an exam at the end of this presentation.
of course. And I'm well known for very easy exams, so it's okay. Okay. So this is a paper on amyloid fibers, where people studied with our system the distance between amyloid fibers that are very important in Alzheimer's. And they measured that the two fibers are separated by 75 nanometers. Okay? Now, what's very exciting is that 3 years later, using PALM, remember that technique PALM that I mentioned to you? One of the co-winners of the Nobel Prize in 2014, Mona, okay, showed that he got with PALM exactly the same value that our customers got 3 years earlier. And why is that important? Because it was the first time that I've ever seen a near-field optical result, okay, actually checked by another technique, and by a very different technique, okay? So I won't go into a lot of this, okay? Excuse me. Okay, I'm going to skip all of this. I'm going to skip the biology. Just let me just tell you why the bleaching that you said in these other tools are not critical in near-field optics. The near-field optics, you shine light one point at a time. So you only bleach one at a time, okay? This is very important, but never mind. I do want to show you one more thing, and then we'll spend 5 minutes on a new technique. Sorry, don't worry, I wasn't going to talk about all of this. But I want to tell you about this. Just give me a second. Because I want to show you Yeah. Okay, this is what I want to show you. This is what is called a quantum wire laser. The light is collected by the probe. You can see this is 0.5 microns. So the resolution is amazing here. This is like, on the order of 50 nanometers. Okay? What's the difference between this and this? 0.8 nanometers, not in space, in wavelength. So the laser mode structure has changed. And you can use two probes, one to measure the distribution of heat and one to measure the distribution of light. And you learn that the distribution of heat is actually buoying towards the P contact. So multi-probe systems have great potential for the future. Okay. So now we can go to the last 3 or 4 minutes. Okay. And that is what is the future. Okay. So I told you that we have a microscope, and a microscope has a Fourier plane. It has an image plane. You can set up a regular microscope such that you can see the Fourier plane. You can see the image plane. And you can even see your probe because it doesn't obscure anything. Now, one of the methods that we used to try and integrate this technology is to take a laser, split it in two, and have one of it illuminate the sample and one of it illuminate through the probe and cause an interference between this illumination and this illumination in the Fourier plane. The beauty of this illumination is that in the Fourier plane, it's a uniform distribution of light. That means what I was telling you, that the light coming from the sample that intersects in the Fourier plane, okay, and not all of them intersect. In this case, all of them intersect with that point. And this is very important because as a result, you can get an exact solution of the 3D structure. Not without problems, like everything, but you can get an exact solution. Okay?
This is something we kind of assessing together. The technology is, of course, the technology of Professor Lewis, but to understand if 3D structures can be realized this way as a commercial product.
Exactly. And I had two excellent students. One was Daniel Honigstein, and one was Jacques Weinroth, the son of the one died a little while ago. And in any event, the issue with such a technique, this is really a holographic technique. This is holography in a microscope with a point source. And the problem with all holographic techniques is that you have an interference between what is called the real image and the imaginary image. This is called the twin image problem in holography. Okay. What we found was, depending on where you put the probe, if you move the probe further in, the overlap changed. This is a very interesting phenomenon because you don't have to change the sample at all. The sample is, yet you are able to get two images of that sample just by moving the probe. Okay? So with this methodology, you could have the probe in one place and image this region and not worry about the interference of the other region. Or you could put the probe in the other place and image this other region. And then you can, in fact, generate the whole image. And as a result of that, if you use two probes, you can, in fact, get rid of the twin image problem. As part of MDM, we're trying to mathematically get rid of it. We haven't succeeded. But even if we don't succeed, we have already resolved it with 2 probes. In addition, and this is a thing I made for Near, okay? As you move your probe up and down, there's another problem in holography, which is called the 2-pi ambiguity problem, okay? And as you move the probe up and down by nanometric precision, you have a very good ability to try and resolve that problem of 2-pi ambiguity. So both the twin image problem and the 2-pi ambiguity problem has a chance to be uh, uh, solved. In addition, what is seen here, okay, in terms of an edge, for example, is well reproduced because you have an AFM which can check whether you are right or whether you're wrong. Okay, so this is what people said when we published. In this issue of Influence Nano, Koenigstein et al. Present a method of quantitative phase measurement. They bring the tools of nano-optical imaging, namely SNOM, there on interferometric detection of phase in the Fourier plane. And then they say, providing data for a new era of physics-based imaging and computed imaging. And there are many good connections to deep learning algorithms because you can keep moving the probe, generate learning sets on known samples, especially in semiconductors, and basically apply deep learning to hopefully get better resolution than what you can get right now, which is limited by the just the fact that you have oversampling, which means you have 2 images which on the same sample, and that gives you a factor of 2 already. You could also use structured illumination, and then you'd even get more resolution. So there are methods to deal with it, but they're complicated methods. And so the bottom line is that today, one of my most important, I think, contributions has been this wonderful company that some of whose members are here today, who work with me day in and day out, and they are really special people who have worked under the conditions of a small company that are not always easy to deal with, especially in situations where research funds change so drastically. And our company is mainly a research instrument company at the present time. And hopefully, but what we are doing today will allow us to move into new horizons of being able to get imaging on very important samples that could have great industrial potential. That's the end.
Thank you very much. Really amazing and exciting. Much appreciated. I have to say, to listen to a lecturer that showed the first article in the world on a certain subject is unbelievable. It reminded me when I did my master, Dennis Gabor came to visit the Technion, and I attended a lecture by him.
Wow, wow, wow.
Also very enlightening.
Very good. It's really.
So thank you, and let us give the team 3 questions, maybe 1 from the marketing team and 2 from engineering. If there are no questions, I will ask. We are, looking for application for our scanning. We benefit now from the fact that semicon has reached the nanometer level.
Right.
And for sure, we would like to find venues for benefiting from your outstanding knowledge and our motion technology. Who would you think are good business partners worldwide?
I tell you something, like it's really really you have the technology that I think can dominate the nanometric motion requirements of many fields. Semiconductors certainly, okay, but there are certain areas, like for example, that physics instrument, for example, deals with. Okay, I think if I understand correctly, there are certain barriers. The barrier, I would say that to really aim for a general market of the use of these systems for these type of microscopies that I'm telling you about, okay, you need not necessarily nanometric resolution. Even single nanometer resolution probably is enough, okay, for PALM and definitely for SIM, which I told you a lot about, and the microscope manufacturers are really the best people to interact with under those conditions. Okay, there aren't companies today other than the microscope manufacturers that are supplying these specialized methodologies of far imaging. But in the near field, I think that what we are doing with Bucher, okay, would be very important for an interaction between ourselves. What we would say is that you need fast imaging, which Bucher can provide us with our tuning forks, and you need fast scanning, which you can provide with your high frequency scanners, okay? One limitation, I would say, is what I spoke to you about on Friday, and that's the Z range. To be optics, you really need to have a larger Z range, okay? And I think that if you can solve the problem of high frequency and large Z range, and techniques such as Bucher, using probes such as ours and our technologies for integrating with microscopes, I think that there may be very good application because you can scan over large regions. And scanning over large regions today with an AFM is very hard. Okay?
Yeah.
So-
What I gave you on Sunday, on Friday, are numbers for the custom high-speed flexure, which can do X, Y in 1 kilohertz and Z in 10 kilohertz flexure. Basically, we can achieve nanometer resolution on unlimited range if the scanning is slow.
Yeah.
So, but I think let's keep it to another discussion, and I think it was extremely informative and enlightening. So on behalf of NanoMotion, I would like to thank you very much. Oded is our general manager. Oded, you want to say anything?
Really interesting. It looks like there are more opportunities than we are looking at now that we need to investigate and see the potential of each one of them. And I think the integration part actually is the interesting one of different.
You can also see I think that it was a good move to make interaction with Bucher, okay? And as I showed you, that your stages are being used in structured illumination, and I think they should be able to be used even more in that field. And if you integrate with an AFM company, you know, obviously I would be very happy to integrate with you. But I mean, there are others other than Nanonics, and you can certainly, I think, make a huge contribution with your technologies in AFM over large ranges.
Yeah.
Okay.
Sounds great.
Okay.
So thank you very much. You know, after this unbelievable presentation, I'm a little bit hesitant, but I'm still happy to reciprocate if you find it interesting.
I definitely wanted, and we will organize it because we've always wanted to interact in terms of a customer, being a customer of yours.
Yeah.
Okay.
Yeah.
All the very best.
Thank you very much.
Thank you so much.
Bye.
Thank you. Bye-bye. Very interesting.
Bye.
Thank you.
Thank you.
Thank you.